Hi, I'm Maciej from HORYZN.
Hi, I'm Azalea from WARR, and together we are
WARR Space Robotics.
Here at WARRYZYN Space Robotics. We are passionate about pushing the frontiers of space exploration and planetary robotics. Our joint team consists of two student initiatives from the Technical University of Munich. The rover, MARRY, short for Martian Autonomous Rover for Exploration and Experimentation, is developed by project creator of WARR Space Robotics.
HORYZN is leveraging its experience in developing unmanned aerial vehicles to deliver the drone for the droning subtask.
In addition to rovers, WARR Space Robotics also develops space elevator prototypes, lunar hoppers, and rover swarms for lunar exploration. For almost 20 years, the team has participated in various competitions, conferences, and test campaigns, where we present, challenge, and continuously improve our prototypes. In May 2025, project creator participated in Robotref in Switzerland, where we won 4th place. MARRY is currently undergoing rapid improvement and testing in preparation for the ERC.
The team is structured into two major divisions. On the one hand, we have WARR Space Robotics, who are developing the rover. On the other hand, HORYZN has dedicated a small workforce to work on the development of the Phobos UAV for the European Rover Challenge. At WARR Space Robotics, we are subdivided into the project management team and then the various technical sub-teams which are working on the different subsystems of our rover. We also have an external board of advisors who are PhD students from the university. They help us by providing feedback, doing our reviews, and helping us with setting up our milestones.
Go ahead, a question. Why do you want to participate in the ERC?
I want to participate in European Rover Challenge because it's a great opportunity for me to apply the skills I learn about autonomous systems in lectures and meet the other teams.
I think ERC is a great opportunity for us undergrad and grad students to gain real-world engineering experience that strengthens our theoretical classroom learning and imposes us key competencies like team collaboration and project management skills that will serve us in any professional setting.
Because I want to go to Mars, so I thought I'd get some hands-on experience building rovers that can go there first.
Our rover is equipped with a robust and versatile drive system designed for navigating uneven and changing terrain. At the heart of its design is a rocker suspension system, combined with a differential linkage. This setup ensures that all four wheels maintain ground contact, even when driving over obstacles, and aids in optimal load distribution. The wheels are independently steerable, providing advanced maneuverability. This includes capabilities like crab steering and zero-radius turning, allowing for precise directional control. These features are essential for navigating in confined or unpredictable environments. Each wheel is fitted with a TPU profile, selected for its flexibility, durability, and shock-absorbing properties. The TPU construction allows the wheels to deform over rough surfaces, enhancing grip while minimizing the transmission of vibrations to the rest of the rover. Overall, the usage of a rocker suspension with a differential linkage, independently steerable wheels, and TPU wheel profiles make this rover highly capable of navigating challenging environments with reliability and precision.
In the electronics team, we are doing hardware and firmware development. For the hardware, we are making our own custom-made PCBs, and for the firmware, we are also writing our own code. We are writing these for STM32 and ESP32 microcontrollers, and we are also using some Raspberry Pis if we want to get some higher computational power. Safety is really important for us, and that is why we use a central power management board, which distributes all of the energy coming from the battery going to the rover. We have 8 K isolated outputs, which helps us give some extra safety for our components like our computational unit, the Jetson, and our drive motors. If we need to, we can press the emergency button, which cuts off all power coming from the battery going to the rover.
To ensure safe operation, we implemented a dual-link wireless communication scheme that combines a low-cost Wi-Fi access point with a long-range telemetry radio. Vital information is transmitted over both channels, and the rover is automatically stopped if both channels are disconnected. This approach results in a cost-effective yet robust solution. Our ground station web UI allows us to monitor vital rover status, define autonomous missions, and to operate the rover in case of autonomy barriers. The usage of web technologies and Docker in our implementation gives us the flexibility to use almost any platform as our ground station. Our navigation stack consists of perception, planning, and control modules. The perception module creates a map of the environment and estimates the state of the rover. This is achieved primarily by fusing depth camera, LiDAR, and velodometry data, which is then utilized by simultaneous localization and mapping algorithm. Moreover, Aruko marker localization provides global reference points for our map, allowing the rover to traverse the desired global coordinates irrespective of the initial mapping position. The planning module is responsible for finding a safe and efficient path to the goal. Obstacle detection helps the rover avoid collisions along the path. Additionally, to increase efficiency, the steepness cost of the environment is calculated and considered in the path optimization. Adding to this, a deep learning model also detects less favorable surfaces such as sand based on the camera feed, guiding the rover away from less traversable areas. Finally, the control module uses 4 independently steerable and drivable wheels for omnidirectional motion control. A 2-wheel Ackerman drive mode is also implemented as a backup in case of drive module defects for added reliability. Our autonomous and manual rover navigation is already functional, and we plan to work on improving robustness and adding fallback GPS localization.
The drone being used for the droning subtask is a coaxial octocopter. We're using lightweight materials such as glass fiber reinforced plastics and 3D printed parts to make sure we fit in the 5 kilogram mass budget. The drone is also equipped with several safety features, such as a manual intervention from the pilot and an auto-landing return to home function when necessary. The drone is also equipped with a downward-facing camera for tag detection during the task. To validate our system's performance, we have also been doing some acrobatic maneuvers and have been setting the rates of the turns for the drone to be appropriate for the mission. So far in our flight testing campaign for the drone, we have been tuning the PID controller through our ground control software to ground control. The next steps will be developing the autonomous tag detection function in MATLAB.
The rover is equipped with a powerful and efficient sampling system designed for collecting and managing materials. At the front, a compact bulldozer mechanism handles material excavation. It's driven by 2 gearboxes, each with an 18:1 reduction ratio, providing the power needed for excavation. The shuttle itself operates using a cycloidal drive with a 17:1 reduction ratio, offering high load capacity needed for controlled swooping and lifting of collected samples. Once gathered, material is transferred to a dedicated storage system on the rover. The storage system includes an integrated load cell, which allows the rover to measure sample mass in real time.
To complete the maintenance, astrobiology, and probing tasks, we've built our own 6 degree of freedom robotic arm. For this purpose, we've also developed our own custom cycloidal gearboxes, which are mostly 3D printed, to achieve a transmission ratio of 16:1 from motor to robotic arm. We've also optimized the reachability of the arm to complete all the different tasks, and we're mainly doing 3D printing and off-the-shelf parts for the arm to make it low cost and reliable. We've also developed a reliable control algorithm, and we're doing imitation learning for the autonomy. This means that we have to perform the task multiple times, and with the camera that's mounted on the arm, the control algorithm can learn how to perform it autonomously.
The drill is mounted to the back of the rover to complete the deep sampling task. It uses a rotating spiral to obtain the soil from a depth of 30 centimeters. The vertical movement is performed by 2 lead screws, which achieves the required depth while keeping the system compact. With the help of a running belt on top of the drills, the system driving both the lead screws, we can ensure that the vertical motion of both the frame and the rotating spiral happens simultaneously. A robust lightweight aluminum frame will protect the critical components inside the drill system, ensuring enough resistance to occurring loads during the drilling process. 2 dynamics motors enable both the up and downwards movement of the frame and the rotational motion of the spiral. A protective cover will be implemented to prevent sand from coming into contact with critical components, such as heat trews and bearings.
We would like to take this opportunity to give a shout out to our sponsors for our components, advisors for their feedback,
And to thank our university for supporting our mission.
See you in Krakow.
Do zobaczenia w Krakowie.